The next step is to calculate the width of the depletion region. Let's look at the physical representation of the p-n junction and label the two ends of the depletion regions as xp and xn. As the charges on the two sides of the junction have to be balanced for neutrality, we can immediately write down the relationship. Na times xp times the junction area is equal to Nd times xn times the junction area. Or simply, Na times xp is equal to Nd times xn. From this point onward, we will normalize all calculation with respect to the area by taking A equal to 1 for simplicity. In the given equation, there are two unknowns, xp and xn, and we need to find another relation between them. To do this, we have to look at the Poisson's equation. The Poisson's equation is written as the Laplacian of the voltage is equal to the negative value of the charge density divided by the permittivity of the material. It looks a bit complicated, but it is only a simple equation relating voltage, electric field, and charge density. In 1D, it is simply the second derivative of voltage equal to minus charge density divided by the permittivity of the material. And you should know that the derivative of potential is simply minus electric field. The minus sign indicates that electric field is pointing in the direction of decreasing voltage. So, in simple words, the Poisson's equation tells us that differentiating a voltage gives a negative electric field. And differentiating the electric field, you get charge density divided by the permittivity of the material. Or working in the reverse way, if you integrate the charge density, you get electric field times the permittivity. And if you integrate it again, you get the negative potential. In a p-n junction, what we know is the charge density, because it is coming from the ionized dopants and is equal to the doping concentration multiplied by the electron charge. If we plot the dopant density along the p-n junction with the boundary between the p-type and n-type materials as the origin, we have the graph shown here. The area indicated by the rectangle represents the total number of ionized dopants. Multiplying this number by Q gives the total charge. And the areas of the two rectangles have to be equal due to charge neutrality. After drawing the charge, we can integrate it to obtain the electric field. This integration is simple and can be done graphically because integrating a constant gives you a straight line with its slope equal to the constant. Going from the negative end, you are adding the negative area so that the electric field is continuously decreasing. After passing through x equal to 0, positive area is added and the electric field increases. Eventually, the total electric field becomes 0 because the area of the two rectangles cancel out each other. The peak of the triangle in this graph is given by the total area of either one of the rectangle, representing the total negative charge or positive charge. But to obtain the electric field, it has to be divided by the permittivity. After we obtain the electric field, we can integrate it again to obtain the potential. Integrating a linear function results in a quadratic function, which is shown here. What we care about is only the total voltage from one end to the other, which is given by the total area of the triangle in the electric field graph. Calculating the area of the triangle is easy. It is just given by the height times the base divided by 2. Adding up the area of the two triangles, we have the following expressions. Fortunately, we do know the voltage across the p-n junction, which is just equal to VBI. Therefore, we obtain another relationship between xp and xn, with all other variables known once the doping concentrations on both sides of the p-n junctions are given. Solving these equations together with the charge neutrality equations, we obtain xp and xn as given here. When we add up both xp and xn, we have an expression for the total depletion region width, which is given here.